On today's episode of Play School for Men, I want to talk about high tensile bolts, which would be things like wheel studs, head bolts, big end bolts, rod bolts, and anything else with a manufacturer's torque specification attached. It's essentially everything that every engineer I've ever met wants to tell every backyard DIY mechanic who thinks he knows it all. I'm John Cadogan from AutoExpert.com.au, new cars cheap, Australia only, website, card. Today's video is really an opportunity to wage war on uninformed nonsense from people who really don't understand the basic engineering of things like threaded fasteners and torque wrenches. And let's face it, there is so much of that authoritative sounding bullshit online in forums and comments feeds. So we're going to lift the lid on that in just a sec. It's all inspired by a question I got the other day from a dude named Mark, who has a pretty legitimate inquiry if you're starting from that near zero baseline of how does this really work. So Mark says, my Tesla Model S has factory specification for lug nut torque of 175 Newton meters as per the owner's manual. At a complimentary wheel rotation, the tyre shop verbally advised that they had applied a 180 Newton meter setting. When home, I checked the vehicle user manual, then returned the vehicle where they backed off and retorqued the studs to the specification of 175. Is over-tightening by 5 Newton meters within the stud tolerance, the torque wrench calibration tolerance, or have the studs been permanently stretched past their yield point? The shop was dismissive of my concern and said the wheels would not fall off. However, I would appreciate your insight. That's from Mark. Well, thanks, Mark. This is a good place to kick off. Now, just to answer your specific concerns off the bat, is it within the stud tolerance? Yeah, it's well within the stud tolerance. Guaranteed they are not damaged. Is it within the torque wrench calibration tolerance? Yeah. Torque wrench calibration is usually within about 4%, I think. So 4% of 175 Newton meters is about 7. So if you get 2 torque wrenches just calibrated and you set them to 175, there's likely to be up to 7 Newton meters variation in what they actually do. So I wouldn't be too worried about that. And have the studs been permanently stretched past their yield point? No. Almost certainly not, but there is an easy ghetto test for that. And I'll tell you what that is in just a sec. Today's video is sponsored by OLIGHT. So check this out. This is one of my favourite OLIGHTs. It's called a Swivel Pro Max. There's a family of these things and this one is the biggest. It's insanely versatile with really solid applications, camping and working in the shed or under the house or anywhere else that's dark and generally inhospitable. And let's face it, if you break down at the roadside and the alternative is changing a tyre on the blackest night ever by Braille, then I'd suggest that this thing is a substantial upgrade. Now they call it a swivel because obviously it swivels. It swivels 180 degrees this way and it swivels 150 degrees this way, so plenty of orientation options, and you can mount it in a variety of different ways. It's got this carabiner so you can hang it over a tree branch or from a cord on the inside of a camper or a tent, and if you can find a steel column or a suitable beam thingo in the ceiling, whatever, boom, there's your mounting option. It's got magnets on the base. If your phone goes dead unexpectedly and you need to get your comms back up and running, it's got USB out, so you can use it as a power bank as well for electronic devices, which is pretty useful. Now, as for lighting options, there's plenty of those. You get your standard white light in a variety of different brightnesses. Then there's red mode for warning and flashing red mode. So if you break down over a crest and you're in a dangerous location and the car can't be moved, this might be a really good option for warning approaching motorists that you've inconveniently stopped in a bad location. This thing is IPX4 waterproof, so it's rated against water ingress. It's quite environmentally rugged, and the plastic is good quality stuff that takes quite a few knocks. I keep mine permanently mounted on the wall just over there because I use it so often here in the shed, where it's a complete godsend. It's yours for under $100 right now on sale, normally $130. I'll have all the details in the description, and thank you very much to OLIGHT for sponsoring this video. If you've got some assembly in pieces all around you, and that could be just as simple as taking a wheel off a car or having a whole engine in component parts all over the benchtop, if you're concerned about one or more of those fasteners and have they been overcranked and therefore permanently stretched, this business about the yield point, okay, the ghetto test is you just get a nut and run it up and down the thread, and if it runs up and down just fine, then it hasn't been permanently stretched. This is how this works, right? The yield point is a boundary in the stretching or other deformation of a piece of steel. It marks the edge of the elastic envelope. So obviously when you pick anything up, stand by. Most people have got one of these, right? They're just your average stainless steel rule. And you can stretch it like that. You know, you can bend it like that, and the top bit stretches and the bottom bit compresses, and then it returns to its original shape. And you can do this multiple times. You could do it hundreds of thousands of times within this envelope of elasticity, and you're not going to change its shape. But if you go too far, some of that deformation will be permanent because you'll go beyond the boundary of the elastic region and you'll go into the plastic zone. And the boundary is marked by a thing called the yield point. That's when the material yields and some of that deformation becomes permanent. And this is just the same when you're tightening up a fastener. See, the whole thing about tightening up a fastener is that you're clamping two parts together by running the nut up an inclined plane, and it stretches the fastener, and the response of the fastener to being stretched is to clamp, right? And the clamping force holds the assembly together. So you want the stretch to be elastic, and it's a really bad idea to use a fastener that has been previously overcranked because it won't be as strong the next time around because it's already yielded, blah, blah, blah. This is a pathway to failure, and you really want to invoke some sort of rational testing protocol on things that you put back together just to make sure that none of the fasteners has previously yielded. And the easiest way to do that is you just get a brand new nut. Okay, so this is a class 10.9 high tensile screw. I don't know if you can see that there, but anyway, that's what it is. It's brand new. It hasn't previously been overcranked. It hasn't previously been cranked at all. But let's say it's part of an assembly and we're putting it back together, okay? Get a brand new nut with the same thread. This is M16 by 2. So you just run the nut up like this, and if it runs up just like I'm doing now, then you're okay, good to go, dude. If it's been stretched even a tiny sort of microscopic amount, 4 or 5 thousandths of an inch, that'll be enough to bind the nut up and you won't get it past a particular point. And if that is the case, what I would do is all the fasteners that go with that assembly, I'd bin them and I'd go with a complete new set. We'll get to the why of that in just a second, but if the budget's really tight, you can replace only one, and that will cure the particular problem of having one fastener that has previously yielded, and you can get away with that. Now, if you want the proper fastener, the grade of the tensile strength is on the head generally, and you can just order one online. The place I go to order mine, and I have no commercial affiliation with this business at all, other than, of course, I spend money there when I want a fastener, like I got this from them. It's Bolt and Nut Australia, and much better than buying fasteners at Bunnings because you can get exactly what you want. If you want a black finish flanged head M16 class 10.9 screw that is whatever length that is, 50 or something, then they'll sell you that. And they'll sell you the same thing galvanized, and they'll sell it to you 12.9 as well, or grade class 8.8, you know, or they'll sell it to you in low tensile, right? Zinc passivated if you want that. Like, they've got it all, and you can only order the quantity you want. It's not like in some engineering outlets where you need to buy a box of 500, even if you want one, sort of thing. So if you only want one, you can buy one. If you want 10, you can buy 10, like that. And they're a great Aussie business. And I say great because I've made several orders from them, and they made a mistake with the last one. They got me the wrong washers, and I sent them a photograph with the washer in the calipers, and a nice bloke on their customer service team named Michael got back to me and basically said, terribly sorry, keep the ones we gave you by mistake. They might come in useful. We've already sent the replacement to you. It'll arrive in the next couple of days. So they're a kick-ass online Aussie business, and they're not paying me to say that. I'm not getting anything out of it. It's just that I spend a lot of time kicking bad businesses in the slats on this channel, and boltonnutaustralia.com.au, they do a cracking job, and you can find whatever you want if you need a replacement fastener for this problem, and it'll be there in a couple of days, right? And you can't ask for more than that, and you know that they've got the customer service to back you up. Anyway, that's the test for the whole, has the fastener been yielded? Just get a brand new nut and make sure it doesn't bind. Now, the reason I say you should probably throw away all of the fasteners, like if you've got 10 head bolts and one of them's yielded, you should probably throw all of them away. That's because the actual tension in the fastener probably isn't that important in absolute terms. Like a whole bunch of engineers' heads just exploded, I'm sure. But what I mean there is, as long as you're in the ballpark, excuse me, it's okay. Like if a particular fastener is supposed to have 5 tons of clamping force to make the assembly work, if it's 4.5 tons, that's going to be okay. And if it's 5.5 tons, that's going to be okay, because of necessity, this amount of flexibility is built into the design. But it's probably a really bad idea if it's got 6 fasteners, like a wheel stud pattern. If 3 of them are at 5 and 2 of them are at 4 and one's at 6.5, that's a bit of a disaster. Consistency is what you're aiming for. And consistency means use the same torque wrench, use it the same way in your hands every time. Like don't do 1 up fast and 2 up slow. You'd use the same sort of pacing. Gentle, quasi-static kind of pull is the way to go with a torque wrench. Hand in the same place on the grip all the time. Like be consistent. This stuff really matters. But another few things that really matter are, especially if you're putting something back together again, if there's paint under one of the bolt heads that you're tightening up and no paint under another one, then that's going to make a huge difference. And if there's rust under one and the others are clean, that's going to make a big difference. And if the female threads that you're putting the bolt into are rusty and gunky and awful for 3 of them and not so much with the other 3, then that's going to make a huge difference as well. And the same thing about lubrication, right? If there's 3 sets of fasteners that are lubricated and 3 that really aren't, and one's really, really rusty, then that's going to make a huge difference too. So just make sure everything is as consistent as possible during reassembly, right? And in the case of those female threads that go deep into things like engine blocks and things of that nature, get the right tap, like the plug tap, and just run it down into the hole and back and blow it out with some compressed air just to level the playing field and make sure that whatever is wrong with any of those threads on disassembly gets standardized for reassembly. That's super important. And the tightening sequence matters as well. Generally with heads, you start in the middle and go out. And with wheel studs, you work on the diagonals. Like if it's a 5 stud pattern, it's 1, 2, 3, 4, 5, like a star. And if it's a 6 stud pattern, it's the diagonals. 1, 2, 3, 4, 5, 6, like that, right? I think I did that right. 1, 2, 3, 4, 5, 6. Yeah, do it that way, dude. Here's the thing that nobody wants to tell you about torque wrenches, right? The torque wrench itself is quite an accurate tool if it's calibrated at within 4%. That's pretty good. But what really matters is how far it actually stretches the bolt. And it can really only get the bolt on target to the desired stretch plus or minus about 25%. And I'm not making that up. I'm not pulling that figure out of my ass. That is a claim made by Ajax, the multinational fastener manufacturer. They make millions of fasteners. They've done the research. They would know. In fact, it works like this, okay? If you've got a really experienced fitter machinist, like a proper Jedi with a spanner in his hand, he's probably good for plus or minus 35% vis-a-vis getting the stretch on target, okay? If you upgrade him to a novice who's had the training and knows how to use a torque wrench, plus or minus 25%. This is not my claim, it's Ajax's. So what we're talking about here is no matter how accurate the tool is, the actual stretch in the bolt is only going to be on target plus or minus 25%, which is still a massive variation when you think about it. So if you're an engineer and you're designing an assembly, you have to factor in plus or minus 25% if it's being put together initially by a torque wrench or if it's being reassembled after servicing by mechanics with torque wrenches. That has to be designed into the assembly process. And the only way you can do that is make the fasteners beefier than they have to be in case they're 25% overcranked. Now, if you want to get better than a torque wrench, you can go for the angular displacement method, because with all threads, you know what they are, you know what the pitch is. This is M16 by 2. It means 2 millimeters in between adjacent peaks of that thread, okay? So therefore you know that half a turn, like 180 degrees of angular displacement, is 1 millimeter. 90 degrees is half a millimeter, etc. So you can snug that fastener up to some notional torque that just takes out the play, like, I don't know, 25 Newton meters or something, and then you can go plus 90 degrees, and that will give you 1 more millimeter. And that's more accurate again. That'll go from 35% Jedi, 25% torque wrench, 15% angular displacement. So that's another substantial upgrade in accuracy, but it's a more technically difficult process to achieve in practice in the field with technicians and service personnel. So, and they have to understand that process. They have to get that training, whereas they've all got a torque wrench, okay? Often they use the angular displacement for a thing called torque to yield bolts, which is where you crank the bolt right to the yield point, which gives it its maximum efficiency, because that's the maximum stretch you can get out of that bolt. Ergo, it's the maximum clamping force, but you don't want to get it wrong and go too far because it's permanently stretched then, right? And we don't want that. So if you want to go better than that, you can use load indicating washers like DTIs. They're usually good for plus or minus 10%. And after that, it's properly aerospace, because we need really accurate measuring systems to measure the direct elongation of the fastener. Or you can, that's plus or minus 3% incidentally. And if you want to go even better than that, you can put a frickin' strain gauge on the fastener and be properly the skunk works about it. That's plus or minus 1%. So that's how to get the range of this thing dialed in from a design point of view. In the automotive space, we're not really talking about precision instruments, right? Or aerospace. We're talking about frickin' cars. So everyone who is a mechanic or a home mechanic has a torque wrench, and they can use it. It's not that hard, even though there's so much misinformation about them as well. But because this is so ubiquitous, that's the way the engineering design is done. Now, if you want to know how much factor of safety there is in these bolted designs to accommodate all of these variables, incidentally, the variables are down to the friction, right? Most of the effort you put in on the torque wrench overcomes friction. This is frictional drag on the threads, frictional drag between the head and the surface that it binds up on, and things of this nature. And that's why consistency and the treatment of the threads and lubrication or not really does matter. You need to get them all the same, because most of the effort is really dealing with the friction, and only the balance is devoted to actually stretching the fastener, which is doing what you want, delivering the clamping performance that you need. So just to put this in perspective, I ran the numbers on the bolts, right? Class 10.9, which is the middle spec of high tensile, which is exactly what this fastener is here, okay? You get 8.8 or 12.9 as well. This one's in the middle at class 10.9 for metric, all right? I'll just show this to you briefly. And now I'll put it up on the screen so you can see it. But the tensile strength of this class of fastener, it's a material property essentially. It's not so much related to the size of the fastener, but I will give you a size example that makes this a bit more easy to digest in just a sec. The tensile strength is just over 1,000 megapascals. Don't worry about megapascals. The ghetto way to remember megapascals is it's 1 Newton per square millimetre. And if you're hazy on what a Newton is, it's about 100 grams. Off the top of my head, it's 101.9 grams, okay? But it's about 100 grams force. Grams force, kilograms force, tons force. I don't want anyone to tell me that you can't use them as units of force. Engineers use that all the time, okay? The Newton is the SI unit of force, but the ghetto hack is grams force, kilograms force, tons force, gets used all the time. Just over 1,000 for the tensile strength. Now the thing about tensile strength is that's kind of where if you load something up to its ultimate tensile strength and you leave the load there, it's gonna break. It's gonna fail catastrophically. And in a tensile sense, what happens is the sample, I used to break lots of samples in a testing lab, the sample starts to neck itself and turn into wire, so it gets reduced diameter, the load just stays on and it runs away and goes bang. And you don't want that. So you've always got to maintain the load below the ultimate tensile strength if you want to avoid a catastrophic failure. About 1,000 for that. About 900 to yield. So you've got 11-ish% worth of margin there for this material, this class 10.9 material. Then there's a thing called a proof load, and that's about 800 megapascals, right? A proof load works like this. You design something and you design it for a particular load, then there's a factor of safety on top of that. And that's kind of, you don't want to exceed where you think it's going to yield or break, right? So what you do is you've got your design load about here, and then you put a proof load on the structure in some way just to make sure that it's going to withstand that. It's the design load plus a factor of safety, right? And the proof load for these bolts, and they test this. They get samples, they test them at the proof load, and they make sure that there's no elongation. So it's going to yield at about 900, the proof load's about 800. But the torque spec, okay, the torque spec is about 70% of the proof load. That's what it's designed to deliver in terms of the stretch of the bolt. It's about 600 MPa, all right? So fails at about 1,000, only designed to be tightened to about 600. That's, you torque it up, and you're 72%, you can go another 72% worth of stretch kind of thing until you get that runaway failure. That's a major factor of safety. So it's very unlikely that in normal operation that you are going to stretch the bolt beyond the yield point. It's certainly unlikely that you're going to break them. In the context of wheels and tyres, when the tyre shop has some fitter with a bone through his nose with an ugga-dugga and he's just for 10 minutes on each stud, it's unlikely that you're going to break the stud off because the machine is somewhat torque limited. What's far more likely in practice is that you're just not going to be able to undo them at the roadside, in which case I would just carry a dirty big long breaker bar. Therefore, just use the high-tech miracle of leverage to get the studs undone. So it's unlikely that even the worst tyre shop on earth is going to yield those studs or break them, okay? But it's highly likely that you won't be able to undo them with the pissy little wrench that comes with the vehicle. So upgrade yourself to a nice long 600mm breaker bar with a 1/2-inch drive and the right socket, and you'll be good to go. Now, if you had trouble compartmentalizing all of those numbers and just passing them through the filter, I made this helpful thing out of a piece of threaded rod. Okay, now this is obviously representative of the proportion of all of those points. Okay, if this is the stretch in a particular fastener, we just magnify it up and have a look at how far it's got to stretch. This is how far it's got to stretch to break. This is how far it's got to stretch to yield. These points are proportional to those numbers that you just looked at. This is the proof load just here. So this is the load that they test it at and make sure that it does not permanently stretch. And this is the designed in amount of elongation we want for the clamping force. And if you do that bolt up properly with a torque wrench, you'll be here, or you'll be here, or you'll be here. Hopefully all of those fasteners will be either there or here or on the money, right? But they'll all be the same, and they'll be so far under the yield point that the fastener has basically indefinite life in terms of the numbers of times it can be assembled or disassembled. And if it does wear out, it's not going to wear out because you've tensioned it up and loosened it off. It's more likely to wear out because of things like spalling on the threads from being done up or undone a billion times, possibly quickly, like in racing. Studs don't last very long because the nuts come on and off very quickly with high-speed guns, you know, and that spalls the threads out from time to time. But they don't wear out because the bolt's been too stretched too often. That's just ridiculous. It's not how this works. You can just see, the thing to remember is this is the bolt unstretched right up here at this end, right? And you got to stretch it quite a long way comparatively. It's a microscopic distance, but this is a proportional representation of the amount of stretch to make it function as the clamp that you need it to function as. And it's been tested to withstand this, and it's not going to bend permanently until you get it here, and it's not going to break until you get it here. And unless you do something pathologically stupid, it's really hard to get it from the design intention here to the point where it yields, or even worse, breaks when you get it here. You do feel it when it starts to break though. We've all had that nauseating sensation when you're cranking on some wrench and all of a sudden the load comes off and you know exactly you're going to be spending the next 25 minutes dealing with a busted off fastener that's just flush with the deck of an engine block, or, you know, exhaust manifold or cylinder head, whatever, you name it. We've all been there, right? And lastly, I just wanted to run you through the numbers, the actual numbers, because these things are amazingly strong. Most wheel studs are M12, and they're probably not M12 coarse thread by 1.75 threads. They're probably M12 by 1.25 or M12 by 1.5, one of those, like a finer thread than the conventional M12 coarse. But I ran the numbers on M12 fasteners from Ajax. All of these numbers are from Ajax, all right? If we look at an M12 class 10.9 bolt, so essentially the same thing as this, only 12 millimeters and not 16, then at the proof load, it's going to be delivering 7.1 tons of clamping force. If you're a bit hazy on kilonewtons, that's just thousands of newtons. 1 newton is 101.9 grams. You can convert that to tons or kilograms if you want. 70 kilonewtons is 7.1 tons of force. That's one M12 stud at the proof load, okay? It's not going to fail till it gets to 87.7 kilonewtons, which is 8.9 tons. That's 4 Hiluxes on one M12 thread. Also not recommended, but these materials, these devices are amazingly strong. They deliver amazing amounts of clamping force. The recommended assembly torque by Ajax is 109 Newton meters for M12. That's going to deliver 45.5 kilonewtons of clamping force, which is 4.6 tons, okay? 4.6. That's a couple of Hiluxes, right? Per stud. There's 6 of them, right? So what's that? So 27, that's, yeah, about 27, isn't it? Yeah, about 27 tons of clamping force holding a wheel on a car if it's got 6 studs. To me, that's just amazing. It's like having a 30-ton hydraulic press on the side of the car holding the wheel on. That's what we're talking about in this spooky world of high tensile bolt design. Most people know how to do fasteners up with a torque wrench. You know, most half-competent DIY mechanics can do that. But I don't think there's any real appreciation out there in the marketplace generally about just how much force is being imposed on these various components. Like 25 to 30 tons is not uncommon just to hold the wheel on a passenger vehicle. And of course, this is why they don't come loose. I just hope that in running all of these numbers past you and showing you a little bit under the hood about exactly how this stuff works, you just understand a bit better what the engineering side of the equation is, because it's built into it. If you're a mechanic, you're forced to operate in an environment where the components were designed by engineers. And the design is there to accommodate a lot of the intrinsic flaws or weaknesses within the system, such as we can all build a really accurate torque wrench. That's no problem, but it's still not going to solve the inconsistency problem when most of the load, most of the effort by everyone who ever gets his hands on one of these is overcoming the friction, which is the hugest variable of all time. And you really have to pay attention, because galvanized coatings and zinc passivated coatings and light oiling, heavy grease, and all this stuff makes such a big difference to the friction, and therefore they have a considerable impact on the stretch in the bolt and the resultant clamping force, and ultimately they have a real impact on how close you get to here or here. And I don't ever want to see you go past here. But to me, you know, if you're dealing with wheel studs or head bolts or things of that nature, conrod bolts or big end bolts, if you're here, that's fine. If you're here, that's fine, especially if they're all here. If you've got 4 big end bolts and they're all here, you've done a good job. But if 2 of them are here and 2 of them are here, not so much. So anyway, I hope this hasn't been the miracle cure for insomnia that medical science has been hanging out for all these years. If you're still awake at this point, well done, dude. Thanks for watching. See you on the next one.